Good evening. Shortly, we will hear an interesting lecture by Dr. Iftach Klap on towards using uncooled low-cost focal plane array in agriculture, challenges and solution approaches. This is part of a webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within the Engineer Association as a cluster of photonic entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage a cooperation both within Israel and with photonics entities in the world. We are open to your suggestions and would love to help foster new local and international collaborations. On September 8th this year, the Berlin-Brandenburg Optech BB Volcanic Research Center and Photonics Israel will conduct an agri-photonics online workshop on advanced agriculture under the ZIM Germany-Israel Collaboration Agreement. We invite you to submit a proposal for short presentations that have the potential for collaboration in research and applications. Please leave your mail address on the Q&A and we will be back with you. My name is Shlomo Glaser. I am the manager of Photonics Israel. Dr. Klap is the head of the Agro, Optics and Sensing Lab in the Agriculture Engineering Institute in Volcanic Research Center. Using optical and algorithmic methodologies, the research is focused on clearing up the bottleneck in optical information acquisition and sensing schemes associated with agriculture monitoring in environmental conditions. Dr. Klap, the stage is yours.
Thank you, Shlomo, for your kind introduction. Now I'll share the screen. Okay. Okay, in the end of it, so actually, one moment. Okay. Okay. Good evening, everybody. My name is Iftach Klap. Today I will discuss shortly our progress toward using uncooled, low-cost focal plane array cameras in agriculture. I will talk about our challenges and the way we attack this problem. So to start with, just a moment, I would like first to make some credits for the people involved. First of all, I would like to thank my students, Navot, Peretz, Shachar, and Omri, and to my colleagues, Yafit Cohen, Dr. Yafit Cohen and Dr. Victor Elchanatis, and to my colleague, Professor Nir Sochen from the Applied Mathematics in Tel Aviv University. So the content of the talk today will be, first I will discuss shortly about remote sensing in plants and how an infrared regime is entered into this task. Following that, we will talk about how to resolve radiometric data from uncalibrated thermal image. And we go on through another topic, which how to use our progress in convolution neural networks to make a super resolution, to improve the spatial resolution of this LOS camera. We give some, in the end of it, some overall end-to-end solution. I mean, to show our a conceptual solution of integrated solution for these two tasks, and then I make a very short summary and conclusion. So remote sensing in the infrared regime. I will discuss first, about issues associated with motivation. Why do we need remote sensing? What is the benefit of using a remote sensing and infrared for our agriculture task? So we need to start, in order to understand this subject, we need to start to understand something about the plant. Well, the plant is kind of a small factory that grabs CO2 from the atmosphere using water from the irrigation and using sunlight in the visible range. He's doing a chemical processing that ends with something that he can make sugar of it. So this is the benefit. This is why the plant is associated with this is how plant is using radiation. So if we now talk about how we do that, this is we're still here with the plant itself. Well, the plants have many small pores on it. It's named stomal, and this is very tiny orifices that it can make a material exchange through it. So it can grab CO2 through it and release water vapors out of it. And while it's very small, it's, as you can understand, very important for the plant, because this is, the way for him to grab the CO2 for the photosynthesis. It's covered from 0.5% to 5% of the leaf, so it's very important to the plant. And we should understand that he got that, in order to have this CO2, but since he is evaporate water out of it, it's also associated with or reflect its thermal condition, because while he's vaporing out, he makes a thermal balance with the environment. So this is where our motivation for sensing coming. Water loss and heat exchange are possibly related to temperature change. This is an hypothesis, and also known as practice. This is the motivation to work with IR. If we know how to measure temperature, we can say something about the metabolism of the plant. We can say something about the irrigation level in the plant, whether we have problems with the irrigation, or maybe the plant have some sort of illness that doesn't let him to get enough water in going up to the leaves. So we can, if we know the temperature of the plant, we can know a lot of information about the plant healthy, and this is then in this stage it becomes a sensing tool for monitoring the stage of healthy and irrigation in the field. This is why we can actually use that. So how can we do that? This is, for instance, an image of a cotton field here in Israel. And as you see, it's very large. Cotton fields in Israel are 300 dunams or 30 hectares, but can go up to 300 on hundreds of hectares. So we need some way to measure temperature in a remote fashion. So what people do, they try to make some remote sensing, and here is the remote sensing operation team of Vulcani, equipped with thermal camera, and then we now go to how we measure the temperature, and probably most of you already know that it's with the using of thermal cameras, and now we discuss shortly why. So we talk first, we already said that the camera, that the plant, make exchange of materials through the leaves, and also exchange of water, and this is associated with temperature measurement. And also we know that the energy coming from this process, this photosynthesis, is coming from the sun. So where is the infrared, I mean? So if we look on the sun, I mean, the sun is like a black body. That means that the energy is associated with temperature through the Stefan Boltzmann process. But if we look on the sun is more associated with the energy, I mean, with the photons in the wavelength in the visible range. So where is the thermal temperature? In the other end, if anyone ever, I mean, pick up a leaf from a plant, you know that the leaf is quite cold. I mean, is more or less in the temperature like a human being. So the temperature associated with the leaves is more like, if we follow the Wayne's law, it's more like in a peak wavelength of 10 micron, which is the wavelength of the long wave thermal infrared. And this is why we're actually measuring in the thermal range, while the energy coming in the visible range. And actually the sun does not disturb us. It's very convenient for us because the entire process is driven by photons in very short wavelengths that we doesn't see in the thermal regime. So it's very quiet. And in the other hand, we can measure. So the sun is driven the entire process, but doesn't make a bother. So here is another spectrum of the thermal infrared. As you can see, we have lot of scattering and absorption from many molecules, but there are hardly no irradiation out in the long infrared, which is in a 10 micron. This is in nanometer scale. So talking a little bit, so what's going on? The situation with radiation or heat exchange is very complex in the field. I mean, assuming that here somewhere in the center, there is a quadcopter hanging a thermal camera, and this camera is focused about this citrus tree. However, there's a direct radiation both on the camera and on the plant. There is a radiation which is scatters in the visual plane, but however, also the ground is heated and heated the plant, and the plant is heated and heated back the ground, and it's making a scattering radiation all around, both in visible and in IR regime. There is this wind that's cooled down the camera. There is this camera, and we talk about this more, that is heated up by the radiation from all around, plus some effect of the wind in convection that cooling down the camera. And there is this wind can be in a different level that's cooling down the plant. And this is all a very complex balance of radiation, which is all the origin of energy of what we observe and the heat exchange both in the camera and in the plant that we are imaging. So our motivation, I mean, is now to making some imaging in this mess. I mean, we know now already now that we want to measure in the infrared regime, and we know that the plant, if you measure in infrared regime through the Stefan Boltzmann equation, we can estimate the temperature of the plant through the emissivity of the plants, which is 0.95. So, and we know that in the other end that it is a complex issue. I mean, the heat transfer in the plant is very complex, so we need to be accurate. And in the other hand, the camera itself is also subjected to heat transfer because it's also in the environment. So it also disturbs what the heat transfer of its own. So now, I mean, regularly, if you want to, I want to make a look about what kind of requirement we need from this camera. So on the left, I present images I got from Victor and Yafit a few years ago. But what you can see is results of experiment they did, and in some point the rows are not well irrigated, and you can see that very well. I mean, in the temperature-wise. So this is what we say, we can use it. However, if you look on the centigrade bar, you see that the temperature are in a very narrow range. That means that in order to distinguish between something that went wrong to something which is all right, we need to be within a very narrow range, which is in a various crop within 2 to 4 centigrades. So our camera should be accurate in this regime. Otherwise, we don't have too much to say about the plant status, because we are the temperature measurement is not accurate enough. Another issue is when we're measuring remotely is the resolution. I mean, if you look on the right side of the screen, you see that there is some point that we can actually see the ground through the leaves. So if anyone have a low resolution camera, and here I made some simulation about that, and we make an image from much higher, you see that as we go higher, I mean, on the left it is the image before, and then we go in scale 1/5 and then 1/10, I mean 10 times higher. I mean, instead of 10 meters, we measure from 100 meters, then this notch is gone. And one of the problems that we are subjected to is that we are subjected to a mixed pixels. This is why if we want to measure from high above, we need a camera with many pixels. However, the low-cost camera or the thermal camera in general doesn't have many pixels. So we have here two challenges. We have the challenge of accuracy in temperature measurement, and we have the challenge of how to make a better resolution for a technology that is now more or less limited to a VGA size, 640 pixels by 480 pixels or less. This is not the visible regime. So we are tackling the both problems, and I will start to talk about from the first, and then I go to the other, and then finally I make some illustration of how to combine this. So returning back to the previous slide, now we only focused on what's going on with the camera. So the camera, well, here in the orange, we're giving some illustration of the imaging. We collect the radiation in the IR radiation through the lens and make some imaging on the focal plane array. However, since the camera, and we want to work with a low-cost camera, the camera is uncooled. So the environment is very aggressive. It's heating up the camera, and there is no cold shield, and there's no really an active lookup table or any method to shutter shut the camera by a shutter and measure shutter temperature or any reference. So what's going on here, that we have a noise source, which is actually how the camera envelope make a radiation on the pixels, and it's a parasite radiation. I want to remind that this radiation is also part of this heat exchange, also containing heat convection with the flow of the wind around, or direct sunlight, or just heating up of the camera because its own electronics. So it's very complex and varies in time, and it depends on the time on the day we are measuring, and the date, and how much time the camera is working, and what is the speed of the drone. So it's very complex and unknown. And this is causing, I get on to what it's causing on, but this is causing to some sort of unknown changes in the readings of the camera. So if we go down and now to a more focused detail to 1 pixel of the camera, you see that the thermal cameras these days, the low cost one, are relying on a microbolometer structure. So the microbolometer structure is basically each pixel have a isolated layer composed of resistance layer and observing layer, and the observing layer is heating up, and then the resistor changed, and then we can estimate from this change the amount of radiation, and back to the plant the temperature of the radiation. However, since this radiation is not only the information but also the noise, there is some additional radiation causing an offset, an additional radiation that causes an unbalanced or unexpected or unplanned, it's more correctly, a heating up of the radiation, which ends up with the gain. So the reading is not only proportion to the radiation here denoted by L, capital L, but also in proportion to the an unknown change in the gain and additional radiation here denoted by capital D, which make an offset. This is so. If we now going more deeper to the image formation, you see now above on the left, I put the image formation in a lexicographic form. That means that the Y, X, D, and N are vectors, which is, we took the Y is the image we take, we represent it as a vector. X is our object, the real temperature we want to estimate. N is the noise, the noise in the camera, shot noise or flexor noise or whatever, all the noises or raw noise or whatever there is in the camera. D is the this offset, and A is the optical response of the camera. That means the point spread function, the blurring of the camera, and G is this gain. So G and A are matrices in this representation. What's important to understand here that Y, assuming that we have 1,000 pixels in the image, so Y have 1,000 degrees of freedom, and X also we have 1,000 degrees of freedom, so as the offset, and so as the gain. And since X, D, and G are unknown, we have 1,000 measurement and 3,000 unknown. So if we want now to make an inverse solution of the problem, we stuck. We have a problem here. We can't really predict what will be X if G is unknown and D is unknown, and X, of course, is unknown, and only Y is measured. So now I want to discuss further what can we do, what kind of manipulation, in optics and an algorithm we can do to try to solve this. So before getting to that, I want to say something about the way, what is expected in the camera. So on the bottom, on the right bottom, you see two distribution, typical distribution measured by Teffelman and colleagues, and you see that on the left in axis symmetry is like the gain, and on the right to it, it's the where you see a sort of a row pattern. This is the offset. So what's really going on after a nuke? So non-uniformity correction, pardon me. So what's really going on? That on the top of what I already said, the gain and the offset are space variant. So we also have to deal with that. So going in addition, this is our measurement around that, and what I want to say before I get to how we tackle that is that here we made some environment chamber. Here is a camera, and we're looking on a black body here in the other side of the lab, but here the black body was much closer when we measured, and we set the black body to 20, 40, 60, and 80 centigrades while changing the temperature in the environment chamber. And as you can see, it never fits in. I mean, the different environment, when the environment temperature were different, the level of measurement was different, though the object was in the same temperature because of this phenomena. So this is the average temperature, and what I showed you before is the distribution. So how we get to work with all of this? I mean, the gain G and D are a space variant, and they are unknown. And this is what I saw. This is why G is here is a matrix, and also we have this flare. And now we want to try to solve it. So our first step towards solving that was to assume that we can make some sort of calibration or knowledge about G. And why is that? Because people tackle these problems with the methods of calibration, making a lot of lookup tables in many temperature, and then measure the temperature and make use a different calibration lookup tables to solve the value. We now want to make, and this measurement are different. I mean, you need to calibrate the D and you need to calibrate the G, and both. And calibrating G is much easier because G, it's the difference in the resistivity, and D is associated with the radiation, which is in a proportion to the fourth order of the temperature. So assuming we can only do the more easier calibration, we only calibrate G. So 1 degree of freedom is closed. So now we only have 2 degrees of freedom and 1 measurement. So what we suggest, let's make another measurement. So, and here is the trick. We're saying that, well, if anyone gets into the thermal constant of the camera, he can realize that the thermal constant of the camera is very long. I mean, in the order of minutes. I mean, if you give the camera a thermal change, it takes time until it actually manifests in the camera. So the snapshotting is very short. I mean, a camera can make a image within 10 milliseconds. So we can assume that if we take 2 snapshots, we will still be within the same G again and the same offset in the 2 images. But if we take 2 images of the same object with the same condition, we get the same image, so there's no information. So for the sake of the extra information, what we suggest is make a small defocus in the camera, because we can do other aberration, but defocus is more natural, I mean, in standard camera. So if we have that, we have 2 measurements and 2 unknowns. So we can solve it back, and we did that and have a result. For example, here, this is a simulation of a raw image. This is one image. This is another image, which is slightly blurred. This is the original ground truth image, and this is the recovered image. And the RMSE error between these is 0.27 centigrades, which is acceptable for the sake of our measurement. Here is another example. Here we make a more severe, I mean, change in the offset and the gain. And this is more sharp. You can see here on the trees, and here you can see it more blurry. The same as here. This is the result, and this is the ground truth, and this is the result. And again, it's within a very narrow recovered error, again with similar range, 0.31 centigrades. This is the reference for that. So then we went on to the more exclusive problem. I mean, assuming that we don't know also G. I mean, we don't know G and D, and of course we don't know X. I mean, we don't know what we are measuring. We know the ground, and we don't know G, and we don't know D. So here I want to first make some sort of intuitive explanation. So above there is these equations that we already showed that if we have only one unknown degree of freedom of D, we make two images of one object. So we use this trick and we say, okay, let's take image of another object, this star object, and make another image. So we have 1, 2, 3, 4 images, and 1, 2, 3, 4 unknowns. So we have n unknowns and n knowns. So it is in generally solvable. However, there's one thing that is more problematic in this scheme, which is that there is a solution for this equation system, but it is within proportion. You don't know about the proportion between G. You need to know the proportion between G and X. So we need some sort of prior knowledge, and we know from the literature that after a nuke, we can say something about the average value. We don't know the values, but we know the average values. So if we have that, we can assume something about the proportion and solve it. Another problem is that you see there is one noise, two noise, a third noise, fourth noise. So each image also subjected to noise. So in order to solve that, we need to solve some sort of minimization of more than 4 images and of 2 objects, here 1 object, 2 objects. And most of the time we use 9 objects, and we solve this maximum a posteriori cost function. We minimize that. To do that, we suggest this algorithm. This algorithm, what it says, it takes the sharp images as a initial solution, and then you got a regression relation between G and D. It solved for that, and then it makes some iteration, and then fix the other part of the equation, and iteratively solve the equation until it converges. This is how it works in general. I suggest to read more, I mean, in the reference below about the details. So what's the way it goes here is that we measure many images of the field, and in focus and defocus, in focus and defocus, and etc. And then we made an estimation of the entire set and G and D together, all jointly, joint estimation. So this is another result of the same concept, and another result with other regime of the unknown G and D, and another one in more close. I mean, again, there is this blurred and sharp, only a few more large size, and this is the restored, and this is the ground truth, etc. Oh, I slipped one. So more or less, so to conclude, we're using this part, we're using some optical manipulation and inverse problem, and we make an estimation of temperature by using some prior knowledge about the average values of G and D and all this information. So this is about more or less now about the temperature. Now I want to return to a slide I already showed 15 minutes ago. So another problem of the camera, well, assuming we can deal with this drift in temperature, we still have problems of resolution. As you can see, again, I remind you that this notch is now, in very high altitude can disappear. And of course, the temperature here, when mixed to our eyes, I mean, this temperature is not true. It's a mixture of the temperature of the canopy and of the ground, which is much higher. So it's something in between and does not reflect what's really going on with the plant. And I remind you that it's very important. So the resolution also, I mean, if you want to measure very fine details, even if the camera is very accurate and you're using very high-end radiometric camera, you still, if you want to go up and measure a larger field of view for the sake of economic, you are subjected to mixed pixels, and that ruin the estimation of the condition of the crop. So how we intend to deal with that? So we developed more than one attitude, and I want to talk about only one of them. So what we suggest to do is to working with to learn how the camera is how to transfer image in a low resolution to a high resolution, and mathematically it means that we want to learn the transformation from lower space to a higher space. So from less degrees of freedom to more degrees of freedom. So the way we tackle this is by developing a regression based on CNN, convolutional neural network. We introduce the system, the way it's done, we introduce the system many couples of low and high resolution, and teach the system how to make this transformation. The way we do that, I mean, in our camera, in this work, is what we develop is a system that the low degrees of freedom transfer to information in a higher degree of freedom by making a deeper layer in a low dimension. What this means is that the calculation done in a low dimension, and this resulted in a very saving a lot of the computation effort. This is more related to another issues in agriculture. Is first that we would like to do things in the real time, and second that we doesn't have always the fastest computers, because I mean solutions also have to be cheap in some way, low cost. So what is done is that in the end of the transformation, we take many layers in low resolution and make it one layer in a higher resolution, and this is done in a so-called shuffle block. And these are a result. So another issue will we make a super resolution in a factor of 4, but a part of just only super resolved information, we also add the denoiser in this process. This because in contrary to RGB cameras, which many times are within 40 dB SNR, the low-cost cameras SNR is 20 dBs or less, and the noise is very significant, and make also quite a disturbance. You can see here that the temperature of this part, which is more or less flat, I mean in temperature, is very noisy. Also, the wall, which is probably have one can determine in a single temperature, probably in a small field of view. So it make also error in measurement. So here, I mean, we show another issues. I mean, you can see here the beginning of the growth, how it looks in original image and or in pardon me, in interpolation, and how it looks like in super resolution. Again, this is another example, and some more examples. I mean, we tested on a very large data set. We use this also on a remote sensing. I mean, also in a close proximity or on a row plans. It's also because, as you remember here, we subjected to some mixed pixels, and we want to allow ourselves to measure from this altitude. So we need to make a better solution. Another example here is against the VDSR, which is another super resolution method in the CNN. And while we are quite well, I mean, these examples we actually looks better, but I mean, in average, we are on the same level, a little bit less, but in aspect of time, our solution is 3% in computing relative to VDSR, which is very important for practical application, pardon. And so on, widths and cucumbers and whatever. So, another example here is, I mean, measuring in horizontally, and this is plant trees. We measure in Vulcani in our yard from 200 meters. And if you look now, this is on the left is the original image as the firm up Opgal made capable to graph. On the intermediate is interpolation, and on the right is our result. And also this is an oak tree for about 40 meters. And again, you can see on the left how the thermals took it, and the interpolation and our result on C. So I mean, we make a significant improvement here. So the last part is short. Well, this is more visionary about how we want to see the entire thing fits in. So assuming we have a low-cost camera and we measure from altitude this vineyard, you see that I mean the images are a little bit coarse, so they are a little bit blurred, and they are also subject to space variant gained and the offset. And we know here in this example, we know the registration perfectly. And the reason we have these lines is because the gain and the offset making a mismatch. And again, it's a problematic for making agricultural decision with this level of information. Suppose now we can correct with our methods the gain and the offset, and afterwards make a super resolution, and then make this orthophoto image or mosaic image, pardon me, we get this. So here we have much more details and we are much more accurate. And while here we are with the root mean square error of 8.2, which is too bad for our needs, here we only have a RMSE error within 0.83 centigrades. This is results are now in a new paper we are writing, which is considered for publication, now considered. So, and this is where I come to the end of my talk. I want to make it very short. I suggest, I mean, anyone who wants to to look more in details about the calculations. They are all now, except of also I mean the super resolution, but the first two methods are published and the super resolution already accepted. So I guess it will be published very soon in Optics Express. And what you are very welcome to look there, and also to write me. I can, or in the end of this talk, I can answer some short questions. As you can see, I mean, we are looking about problems that associate with real life. So if anyone has ideas of how problems like this or other problems in acquisition associate with measuring environment can fit in with something he is doing, we are very open to collaboration, both with the industry. I mean, in the other project, we have in super resolution, we have some collaboration within the industry, and also with other research group, of course. So to summarize and concluding my short talk is the remote sensing demands for radiometric level data. I mean, very accurate in temperature-wise, and also need higher spatial resolution. Otherwise, we are subject to mixed pixels, and the temperature is not correct. I mean, it's not reflects the canopy. It reflects something between the canopy and the ground, which is very, I mean, urgent problem. What we are trying to do is using simple optical changes like focus and defocus, and relying on heavy post-processing to make to stabilize the system, and first with an inverse problems, and also with the learning problems, some more classics, some more from the latest time, like the convolutional neural networks, all the tools available to make a solution that can rely on a low-cost solution. Cameras that coming with the problems and we solve it. So our future task here is first to extend our work to the situation when the G and D are are changing. I mean, and we can, I mean, the average, I mean, and we have also already have a direction to that I skipped here from the sake of time. And of course, a full end-to-end experiments, which is, I mean, will conclude this research. Okay, I thank you for all of these who listening to me, and I'm open to questions.
Okay, thank you very much, Dr. Clapp. And now you can read the questions in the Q&A, or you like me to read for you, and then you.
Okay, no, I see. I see them. What is the required accuracy of temperature measurement? Okay, so well, it is. I mean, it's for how much we know. I mean, I am working with very close collaboration with two other researchers in Vulcani Center, Victor Elchanatis and Yafit Cohen, which is doing with data mining in this regime. And for what we know, it is within 2 to 4%, 2 to 4 Celsius centigrades. Okay, no. Okay, answered live. Is it another question? What is the, okay. What, okay. Is it necessary to measure the absolute temperature or relative temperature is sufficient? Okay, so, well, it is important to measure the absolute temperature, because this is what I begin with. The entire thing is that the plant is a factory. When plant doesn't have irrigation, it closes this stoma pores, and this is for instance, in one example, why it become hotter. So you need to follow the plant's physics in order to make a correct evaluation of the plant condition. So it is all absolute, because, I mean, plants living in a very certain range of temperature, like ourselves, we cannot live, I mean, in 70 centigrades. So this is very much like measuring temperature of human being in this aspect. You need to measure the favorable temperature of human being in order to know what is the condition. Okay, so the next question was, what wavelength is preferred, mid wavelength IR or long wave IR? So again, since we want to estimate temperature, and the plant is within 300 Kelvin, that means that following Wayne's law, or it is easier, I mean, following the black body model or Wayne's law, the peak radiation of the plant will be in 10 microns. So we need a long wave IR for this. Okay, answered live. Next, with the VGA size, what is the preferred distance to look at the plant? Whoa, so a VGA size is 640 pixels by 480 pixels. And also it is, the question is, I mean, we need, now what you're asking is, what is the ground distance sampling actually? I mean, what is the conversion of the pixel size in the camera into the ground? So if the pixels of standard thermal camera is 17 micron, and the focal length of the camera is about, for make it easy, 17 millimeter, that means that the IFOV is 1 milliradian. So if you want to look on phenomena of the size of 10 centimeters, you need to at least be as far of 1,000 times 10 centimeters is 100 meters with this camera. However, the question is also of the field of view, because we want to use a shorter focal length, or to look from a larger distance, because when measuring a field, we want to cover the entire, I mean, the entire field, which doesn't cover within, I mean, if you have 640 pixels of 10 centimeters, in each frame, you cover about 6 meters, which is not very much, I mean, in the aspect of field. We also had, in the end of the day, we need to survey the entire field, and we also need to make some, many times, 30% overlap between frames in order to make a mosaic. So we need to, I mean, we need to go up to the altitude. So many times we need to use something like ground distance of sampling on the ground of 30 centimeters, which is more or less what is done in row crops. And this depends on, I mean, on the application. Okay, answered live. Okay, going on. What is the required sampling resolution in terms of unit length in the plans plane? So I think I make the answer already. The way it's done is that you should calculate the ground sampling distance, which is within a triangular relation with the pixel size and the focal length. And the other part is the distance from the camera to the target. So this is more or less a triangulation issue. Okay. Okay. I think this is the last one. is there an option to calibrate the camera with the black body that will be on the field? Okay, so I mean, actually we bought a huge black body, which is 30 centimeters. And I know that once there was a much larger black body in a yard or in EORD in the Technion, and maybe now in yard in nearby Haifa. Anyhow, black body as analytical instruments, they are, I mean, they are quite small. And again, 30 centimeters for, if you follow the calculation I made, I mean, is that it's 1 pixel. So maybe you can measure for a closer range. So it covers a few pixels. But we have 640 or a few hundred by few hundred pixels that we need all of them to calibrate. And in addition, we're not always in a situation that we can calibrate, in the aspect that we want to be in a situation that a farmer or a service company can hang a camera on a drone and make a survey and end with that it will send the results. We don't want a technician involved, because it makes the entire operation much more expensive. So a black body on the ground is too little and very with a lot of burden. I mean, and we are after maybe, I mean, we want to make some new technology, but to solve a practical situation. So we need to solve up the calibration somewhere in some other means, in some way that you can make maybe a 2-point correction before you fly up, and then the system can work on its own. Okay, so I think I answer all the questions. If anyone has another question, if I have time for that.
Omer Cohen provide you some information about Opgal thermal, some kind of camera. So if you looked at the last Q&A, you will find this information. But it's only information. It's not a question.
And I don't see.
It's Opgal thermal APP-TH camera, measure temperature without any need of calibration. That's the information we provide you.
Okay. I say that we are working with Opgal and also in super resolution. I didn't check the stability of Thermap TH. And also I'm working with the guys from Opgal. So I wouldn't want to say anything that, I mean, not 100% checked. So we know this camera. I cannot say much about its calibration, and well, probably, I mean, it's I guess it depends about how they work with the camera. Let's see, because I mean, if you look on the literature, and I don't say anything about the Thermap because I didn't check it, but if you look on the literature, there are a few survey done on the low-cost thermal cameras. Not I didn't see one on the Thermap. How they work in field condition, and there is such a problem. There is a problem of calibrating them from all kind of brands. I mean, so if whomever gives this note, I didn't see this, pardon me. I suggest him to look for, I mean, this literature, because there are many people which are bothered with that. And well, I hope that Opgal solve it. Yes, of course. Did you manage to extract information regarding the microclimate around the plant from the focused defocused image? I'm not sure I understand the question about the microclimate. Well, we didn't make measurement of microclimate, so probably the answer is no. For example, air temperature, wind pressure, air moisture, etc. Well, there's something that is a little bit, it's another question. For the same one, okay. Okay. So now I understand it's in two parts. No, we didn't make a measurement of this kind. To this end, we are more or less focused on algorithm, on the aspect of accuracy, and not in this part of the project. It's not yet applicable. In super resolution, we did a lot of measurement. Outdoor, indoor, whatever. So okay. So this is the question from the third guy. I don't see any note from anyone about the thermal camera. So, okay. I can just say that I really like the guys from Lopgal, and I suggest everyone to work with the Israeli-made camera. This is, we support that.
Okay, thank you very much, Dr. Klapp. It was very interesting to hear about the way of measuring temperature under these conditions. And we hope for the future to get much more information. Maybe we'll find some collaboration out of this presentation.
Okay, thank you very much.
Thank you very much.
Thank you.
Okay, goodbye.
Goodbye.